So I'm going to try, in this talk, I was trying to decide how to structure it for this very diverse audience. So I decided to kind of follow the computer science tradition of giving an overview of a lot of papers. I know that's sometimes a little frustrating to economists who are used to going into a lot of detail on a single paper. But hopefully on the upside at least, you'll get a little bit of a sense of why I've been working on a collection of disparate topics. And I think it's really the spirit of market design that you go in to answer a question and you have to bring in tools from lots of different disciplines to get the right answer. And so you maybe get a little sense today of why I'm proving central limit theorems and doing network theory and all sorts of other crazy things, all in sort of pursuit of a goal. So in the co-authors on the work I'm talking about today include Dennis Nekopolov, who's here, Hito Embens, who worked on some of this work together with me at MSR, and he's now working at Amazon part-time. Also, Stefan Wager is a graduating PhD student in statistics, brilliant student, and Dean Eccles just moved from Facebook data science to a faculty position at MIT. So, everybody here is excited, I'm sure, about the recent advent of marketplaces and auction-based platforms, and nobody here needs more motivation that market design matters in these settings. One of the particular type places where the extra sort of oomph of sort of theory and generally social science tools is really important is distinguishing things that have different effects in the short run and the long run. So in some sense, it's pretty easy for businesses to make good market design decisions when you do something and you see the effect in the short run, which is predictive of the long run. Then, even if you don't have any training at all, you kind of discover it, you see it in A/B tests and short-term experiments, and you kind of don't screw it up all that often. The places where you can sort of massively screw things up and send an organization, innovating in the wrong direction for years, and that applies actually to all of the major tech firms we all know and love. They have areas where they innovate in the wrong direction for years, are the places where the short term and the long term actually give you opposite conclusions. But it's actually fairly common for especially advertising marketplaces or e-commerce marketplaces where you have sellers and buyers coming together. So just to give a bunch of examples, I had a guest speaker who used to be a VP at eBay who came in and told a whole bunch of these stories of how he somehow used data to get eBay to do some of these hard decisions, but things like eliminating listing fees or making posting pictures free. Economists understand immediately why that might be a good idea, but you're walking away from a couple $100 million in revenue in each case. So the short term looks very, 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 very bad. And you have to have the economics to put it into the long term. Things like changing the search algorithm to emphasize price or force sellers into more uniform categories, emphasizing, prioritizing people who have low shipping costs, and so on. All of these are things that have different effects in the short term and the long term because the sellers respond. The search advertising examples are maybe less obvious if you're not into the nitty-gritty, but in some sense even more insidious. There's basically a very easy way to make a whole lot of money in search advertising. So you've got all these advertisers who are putting in ads, and some of them are putting in $100 a click for asbestos-related queries and $30 a click for auto insurance-related queries. And then you've got toothpaste-related queries that are worth 4 cents. Okay? And you have all this big database of advertisers, and they've put their bids in that database. So if I change my algorithms in a way that accidentally, or maybe accidentally on purpose, drops a few auto insurance queries onto ads onto toothpaste queries, okay, boom, you've just made $10 million, $100 million. You've made $1 billion if you're looking at the overall, say, Google search revenue, and it looks beautiful in a short-term test. If you just look at revenue, just taking those auto insurance ads and putting them on toothpaste queries is going to make you a lot of money. Now, and any economist sees immediately that this is not a long-term solution for making a lot of money because, of course, why? Well, there's incentives. The auto insurance advertisers will notice that they're not selling a lot of cars on the toothpaste queries, and so they will lower their bids. Okay? But it turns out that actually measuring and documenting that is super hard because advertisers are heterogeneous, they respond at different times, things are very noisy, and so on. So This is a problem that basically, like, especially say when Yahoo was under pressure before they shut down their search engine, they basically ran down their quality month by month by month by month over a period of 3 years until their prices went down by like 30%. Because every month they just make things a little bit worse. They cheat a little bit, put a little bit of those high-value ads onto low-value queries. The numbers look great this month, and you don't pay until next month. And if you're worried about getting taken over, if you're about to quit, all sorts of things, you do that. And so that group of people actually got very, very good at cheating the system before, but under high pressure from the management. Another example is just changing pricing. Okay, so again, as an economist, the whole reason the whole theory of auctions and mechanism design and so on is all about like revenue equivalence theorems. Those are based on people changing their bids and responding. But surprisingly enough, the practice really has a hard time taking all of that into account. So, of course, a theoretical framework is a key. And so even though I'm not doing that much microtheory myself anymore, I just want to really emphasize that I've never stopped for one moment being a believer in the huge power of economic theory to understand all these things, because you need to have a very strong understanding, belief, and conceptualization of what's going on to understand why you walk away from $200 million of fees of people posting pictures on eBay and so on. And some of the things will never be really possible to fully measure. And so that belief and that conviction and the theory and the experience all plays a really important role. But at the same time, these are very data-driven businesses, and so you do need to try to bring data to bear on these questions as much as possible. So, how can data help in these situations? Well, data can inform what kind of designs will work better or worse in a range of environments similar to the existing one fairly easily. So if I'm thinking about modish changes, if I'm thinking about changing fonts or doing small things, then I can just very easily look at data and it'll tell me about small changes. The hard part is when you're going to change the world a lot. And then you need a much more sophisticated analysis. So experimentation actually is this real mixed bag. So experimentation is, the way that all changes get made. I'm sure everybody here knows that there's, 10,000 experiments or so run a year at Google. Everything that changes, the smallest change in the code, goes through a randomized controlled experimentation process. This is crucial for the speedy innovation of all of these high-tech firms, because an intern can propose a change, put it through an A/B testing platform. If the numbers look good, it can ship immediately, and that's how you can make changes to your product every single day in a highly decentralized way. So experimentation is like the heart of rapid innovation. But people get seduced by it and end up misusing it and misunderstanding it, especially people who aren't really used to thinking about economics and economic theory. So short-term experiments, by definition, can't show long-term outcomes and feedback effects. And I'll show you it's even worse than that. In the standard practice at all the major tech firms, has like just really idiotic flaws, but that somehow remain standard practice. So, so I'll talk about advances in experimentation that they're sort of at the cutting edge right now in theory, in academics and in practice. Another way that you can get around it is to try to get insight by analyzing heterogeneity of effects, and so that's one focus of my research. Another approach is to actually use what's really the standard toolkit of empirical economics, which is to use what we call structural analysis to estimate people's underlying preferences, essentially calibrate the theory model with data. And once you have all the parameters of the theoretical model, you can do counterfactuals. You can say, what happens if I switch to a Vickrey auction? What happens if I change prices? And so on. Now, the problem I have with my first round of that I did with Dennis is that we did great on like a small set of very high-value keywords where advertisers were super rational and were maximizing all the time, but we kind of flopped when we took our model to the broader spectrum. And so the final paper I'll talk about today is work in progress. We have where we actually use a Bayesian model to estimate the preferences of bidders, and we have a much richer set of objective functions that we measure. So the work I'm going to tell you about today basically then was going to fall into a couple of categories: advances in the theory of experimentation, advances in machine learning, and bringing machine learning together with econometrics to estimate heterogeneity effects, and then finally kind of a large-scale application in a large-scale Bayesian model of the traditional sort of economic approaches. So we all know about A/B tests, randomized controlled trials. We're going to take users, put them into treatment and control groups, look at their outcomes, and use that to decide whether I ship a new algorithm. And the way that this is commonly used, like Amazon or eBay or Google, would be that actually the treatment is going to often a new algorithm. So there's like one algorithm for ranking results and another algorithm for ranking of results. And you're going to test how those algorithms perform. So they're not like isolated experiments where you're just changing one little thing and figuring it out. You're testing complex algorithms, which is one reason that people often don't understand, like when they accidentally on purpose put up auto insurance on toothpaste, it's because they tested like 50 algorithms, but the one that happened to put up auto insurance on toothpaste by mistake is going to have the best revenue numbers. And so that's why you systematically innovate in the wrong direction. You're selecting things that look good according to a set of metrics. So just to see like exactly why things can be so bad in a sense, the standard industry practice, the easiest thing to do if you want to test a new algorithm is that you take either a subset of users, like you track cookies and take the users, or you take a set of page views. So the same user as you do subsequent searches might be in different groups. So either page view or user, but it's really at the user level. You're going to give some users one algorithm and some users another algorithm, and then you measure revenue and user experience. And you have maybe 4 or 5 key numbers that you look at to decide if this algorithm is an improvement or not. So it might be good for the user experience, a little bit bad for revenue, and you'll make trade-offs along that line. So there's multiple errors in this if you're thinking about the revenue number in particular. The unit of experimentation is not the unit of analysis. So if I'm experimenting on users, any particular seller on eBay or seller on Amazon or advertiser on Google will see only 1% or 0.5% of their traffic in the experiment. So if I'm an advertiser advertising on auto insurance, and in 1% of my traffic, I'm getting some ads put up on toothpaste, all right, I'm not really going to notice that. So there's the issue that it's often a short experiment, but even if it was a long experiment, as the advertiser, I don't even know I'm being experimented on. I don't know how I'm being experimented on. I might just see a little noise in my data, but I certainly am not. The results of this experiment are useless for the counterfactual of what would happen if you applied this algorithm to all of my traffic. So if I want to know what happens to an advertiser if all of my traffic sees my auto insurance ads put on toothpaste queries, this experiment doesn't shed any light on that whatsoever. Yet this is the standard practice. So what are all the other mistakes? Well, the interaction effects between the bidders are thus ignored because the advertisers themselves aren't being stimulated. It might be that if something like this, some experiment increases prices for an advertiser, for all advertisers, some advertisers might hit budget constraints, then that's going to affect the other advertisers. So even before you get to strategic considerations, you're going to see very different outcomes when you release the thing to the whole platform as when you did it for a particular user. Then there's, of course, the game theory part that they actually might respond. They might respond just to their own situation, and they might interact with one another. And then finally, the thing that's probably most important for marketplaces is long-term participation, and that's totally ignored. But yet, we operate all of these platforms in exactly this way. So I think the e-commerce platforms can do a little bit better because it's easier for them to segment their market into product categories. So there is some history and process of experimentation, like at the product category level at the eBays and Amazons. It's actually much harder to do for reasons I'll show you a minute in search engines. The other thing people sometimes do is New Zealand. So you know that basically like every platform, releases things first in New Zealand and they see what happens. So, but you don't have much of a control group and so on when you do that. Okay. So some of the cheaper fixes, and this is kind of, a bit of the state of the art that's motivated by theory, but still doesn't really slow down your progress or change things fundamentally, is to modify the evaluation criteria. So for example, when I'm going to decide whether to ship an algorithm, I've got some numbers I'm looking at, and I might measure revenue. And that seems like if revenue is what I care about, I should measure revenue. But if you're an economist, you realize that no, you shouldn't measure revenue because some of that revenue is not sustainable revenue. It's not equilibrium revenue. So particularly the revenue from putting the auto insurance ad on a toothpaste query is misleading revenue. I book it in my experiment, but it's a bad prediction of the counterfactual of what would happen if I shipped it to the rest. So one of the things that I did early on at Microsoft was suggest that you throw away money that you made in a bad way, and you don't even count it when you evaluate your experiments. Okay? And so by measuring something that's not actually what happened now, but a better predictor of the long term, you get a better answer. And you also diminish the incentives of engineers to try to test algorithms that put auto insurance on toothpaste, because they know that they're not going to get credit for that type of thing. So there's a lot of variance of that. Another thing you can do is do a small number of long-term studies to relate short-term metrics to the long term. But this has its own problems, and it's somewhat limited in scope. And then another thing you can do is add in constraints that protect advertisers. Like I know at Facebook there's these Zuck rules. So there's experiments that you can't run. You're just not allowed to do that. And you might say, you know, in search, maybe I'm not going to ship things that affect any advertiser too badly. Like if you're going to give some advertiser a 300% price increase, go back and fix it. You put in rules or restrictions. And so this is one kind of heavy-handed way to try to keep things under control, make sure that you're not predicting that you're hurting any of your sellers or advertisers too much. But this is also a very crude approach. So now we can get into the more expensive solutions and the solutions where there's more of an active research going on to try to get these to work better. So the first thing we could do is we could actually experiment at the advertiser level. So I could give some advertisers a price increase and others a price decrease. Now that's actually much harder than you think, because the advertisers are actually competing in an auction. So your pricing mechanism, you're not just setting prices for people. There's like a marketplace. And if you think about what's happening on Amazon or eBay, you know, what you're doing is you might change a search algorithm, and that's, you know, if you put one seller up higher, another seller's down lower. So it's actually, like, technically, conceptually, sometimes hard to think about how do I shock one seller without shocking another seller, because one better, the other worse, you know, one brighter, the other less bright. So there's some tricky things about that, but you can imagine trying to do a smaller set of them and finding them and looking at the graph and trying to find people who are isolated from one another to do that. That can be kind of tricky. So here's just some examples. So suppose you're on eBay and you shop for How to Train Your Dragon costume. There's going to be a certain set of, so this is for my daughter for Halloween, there's going to be a certain set of sellers that compete for that query. Then I might look at Frozen costumes, and I'm going to have some kind of, you know, sellers that sell princess stuff, and I'm going to have other kinds of sellers who sell Halloween costumes competing on that query. And then I might go to How to Train Your Dragon toys, and there's going to be people competing on that who sell How to Train Your Dragon stuff, but also other stuff. So essentially, you know, e-commerce markets are bipartite graphs where the degree of competition one seller or advertiser has with another is determined by which user queries they compete on. And of course, once you realize that, you realize that the whole graph is connected. So there really aren't any isolated sellers. And so then you have to get into the world of engineering. I think it's actually not surprising that some of the early papers in network experimentation were written by computer scientists like Ugander and Kleinberg and so on, because they were maybe a little more willing to make compromises than some econometricians and so on, who tend to be more purists and kind of stop when we can't get the right answer. But so one paper I've written in this area is to try to test interactions. And so the application, this has applications for general social graphs, but the application in e-commerce would be, maybe I can test the hypothesis that people who are removed from each other by a certain distance don't really affect each other. And then if I could reject the hypothesis that they affect each other, then I could actually, you know, give me some guidance to how to cut my graph, and maybe I could safely ignore some interactions. So that's one application of the theory. This paper is really a statistics paper. And the question is, how do you do inference properly for various hypotheses in a network setting where everybody competes with everybody else? So let me just tell you briefly, like, what is the statistics problem? Well, the statistics evaluating experiments or anything else almost always relies on independent observations. You have a bunch of IID draws from a population, and then you have a theorem about what happens as n goes to infinity. Now, there's two problems here. One is that people aren't independent. They affect each other. And second, the problem is that, what do you mean n goes to infinity? Like, I have the eBay graph. You know, there is no bigger eBay graph that this is a sample of. You know, I have the MIT student graph for my experiments with Bitcoin. You know, I'm not interested in a hypothetical universe with MIT being 3 times as big. Like, I have the MIT graph. So there's a branch of statistical inference for hypothesis testing that deals with some of these problems, and it's developed by Fisher. It's called permutation tests or randomization inference. And that method allows you to do exact hypothesis tests without n going to infinity and without assuming correlation. But it's not used all that often because it's very limited in scope. It can only work for to do what's called sharp null hypotheses. So if I think of a sharp null hypothesis, that's a null hypothesis where under the null, I know what your outcome would be under any alternative distribution of other people's treatment effects. So imagine we're a network here. If my null is there are no treatment effects and there are no interaction effects, then under the null hypothesis, I could permute the treatments of all of your friends, but under the null, your outcome doesn't change. And because of that, I can generate a statistical distribution. Suppose I took my test statistic was the difference between treated units and control units. Well, I could generate the distribution of that test statistic by redrawing the treatment assignments. I can imagine re-randomizing you, and under the null, the test statistic, I would know exactly what your outcomes would be if I re-randomize your treatment assignment. But that doesn't work for interesting hypotheses like network effects, because, for example, if my null hypothesis is that there's no peer effects, but I want to allow that a treatment has an effect on you, like if I change your price, you're allowed to respond, then it's not a sharp null hypothesis anymore. Because if I changed your treatment assignment, I don't know what your outcome would be. And so I can't construct this randomization distribution. So the novel insight of our paper is we figure out how to transform non-sharp null hypotheses to sharp null hypotheses. And we basically do it by throwing away some of the data and defining a new experiment. So I'll just show you a quick little picture of this. So here's a network. The yellows are treated. The yellow boundaries are treated. And so what I want to do is figure out the effect of friends on me. So what I do, instead of studying all the units in this network, I'm going to pick just 2 units to study their outcomes, focal unit A and focal unit B. Then in this network, I'm going to say, if I want to test whether friends of friends matter, but I want to allow that you being treated matters, and I want to allow that your friend being treated matters. What I'm going to do is I'm going to take this guy and this guy, those are my focal units, the ones I study. Then I'm going to define what I call buffer units, and that's all the direct friends of the buffer units. And I'm going to hold their outcomes fixed. And then I'm going to think about, well, okay, what's left are friends of friends, people who are friends of my focal units, but aren't friends of any of my focal units. And they aren't focal units themselves. Those are auxiliary units. I'm going to then think that these guys, I'm going to re-randomize their treatment assignments, and that's going to generate a distribution. So for each of my auxiliary guys, I'm going to think about redrawing their treatment assignments. And under the null, those redrawings shouldn't affect the outcomes of my focal units. So I can therefore construct an exact distribution of the test statistic, which is the test statistic looks at how outcomes change as a function of my friends of friends. And so using this, I can actually, without taking asymptotics of a network, I can do valid statistical inference on whether or not friends of friends matter. Okay. So this is kind of a fun thing, and again, the motivation for me working on this was I wanted to be able to sort of rule out some complex interactions, and if I could rule out some complex interactions, then possibly I can do my econometrics of my network and measure things. Okay. All right. So that's one approach. I'll just mention briefly, there's an approach that I've been working on in practice. I haven't published anything on this yet, but it's been worked on by my new Stanford colleague, Johan Ugandar, and he was at MSR last year. So one thing that you can do is you can try to divide up a network into communities. There's still going to be spillovers. And then you can actually randomize, not at the individual level, but randomize at the community level. And the interesting statistical problem posed by this is that some people are, and the reason you do this is you're trying to approximate the counterfactual of what would happen if all my sellers were treated. But of course, there's going to be some sellers, like this guy, who has about an equal number of friends in a control community and a treated community, because some people are going to spill over across communities. So even though I did a randomized experiment, there's actually non-random assignment of individuals to being fully treated or fully controlled. If you're someone with lots and lots and lots of friends, you probably have an intermediate number of friends treated and controlled. While if you don't have a lot of friends, you're more likely to be fully contained. So some people are having all their friends treated, some people are having none of their friends treated, but people with lots of friends are having an intermediate number treated. So there's a statistical problem then of how you analyze this data where you did random assignment, but you don't actually, you have to treat it as if it was an observational study, because the individuals are not randomly assigned according to their network structure to having to be fully treated and fully controlled. So it's something I'm working on. All right, so then another approach is well, I'm sorry, this is just a summary of what we just did. So there's two more approaches that I've been working a whole lot on in the last few years. One is to try to gain insight from your short-term tests by studying heterogeneity of effects. So I can basically try to look out and see, okay, which advertisers were affected a lot, which advertisers were affected a little, which ones were affected positively, which ones were affected negatively, and then use that to try to understand what the long-term predictions would be. This is going to be qualitative and directional rather than exact. And then the thing that will give you exact answers, but it's going to require a ton more assumptions, is to build a structural model and try to make a full prediction using a theoretical model. And I think of these things as complements. You can tell people a little bit qualitatively and then show them this more complicated model. I should say, though, that these types of more complicated models are not that successful in practice because the computer scientists and engineers and so on aren't familiar with them. So they're harder to use in practice. People don't like all the assumptions. Even if it's better than, you'd think, well, gosh, if you could compare like doing a user level experiment and using a complicated model, maybe you'd like the model, but that's not how it works in the real world. The one place where these kinds of models are very successful in practice is for pricing. So any consumer packaged goods product, any company that does a lot of consumer pricing uses these kinds of models. Okay, so let's talk now about heterogeneity of effects. So there's a lot of concerns about, in general, if you want to try to understand whether a treatment had heterogeneous effects, there's a problem that if you try to kind of look at, if you have lots of covariates, you could kind of do data mining in the bad sense of data mining. You might look out and find that, okay, I'd say I did an experiment on a drug. There's guys between ages of 62 and 64 with this pre-existing condition, and they have a really strong positive treatment effect. But of course, there's a multiple testing problem. If you keep fishing around for some group like that, eventually you'll find it, and that's not valid. Which is why the FDA prohibits that. It's illegal. You have to specify a pre-analysis plan. You have to specify in advance all the heterogeneity you're going to look for. Now, if anybody's from the machine learning community, that seems crazy. Like, how would you possibly know if you had hundreds and hundreds of covariates what all the interactions between those covariates and a treatment would be? So the goal of my research here is to be able to use machine learning techniques to look for heterogeneity, but to get out on the other side of it, valid confidence intervals. So in the A/B testing world, for companies, they really look hard at actually the statistical hypothesis test. Like, was this significantly beneficial? They're going to actually not even put numbers on a scorecard if they're not statistically significant, because they don't want to confuse people. So it's very important to get confidence intervals out for your estimates. And that has not been the emphasis of the machine learning literature, and so that's why I'm going to take some very standard algorithms, but be the first one to actually deliver results on them, because the machine learning literature never cared about this. I'm like, how can it be that like hundreds of thousands of papers use random forest and nobody ever asked if they were asymptotically normal, but nobody cared, it turns out. So, and it's actually pretty hard, but that's one of the things we solved. So we're going to do two different types of heterogeneity. They're related, complementary. One is that we're going to look for segments or subgroups. So that's going to be based on regression trees or recursive partitioning. And what that's going to do is I'm going to take the data, I'm going to divide it into some groups, maybe like 10 groups or 5 groups, the data is going to tell me. And within each group, I'm going to estimate a treatment effect. Those are going to be interpretable. They're not the best for prediction, but they're going to be very good for getting valid standard errors and that are very reliable. Because I could have 10,000 covariates and 1,000 observations. Basically, no existing statistical method is going to be able to give you a good estimate in that kind of environment. But I can still, with my method, I'm going to tell you, divide the data into 3 groups, and here are the treatment effects in each group. And I'm going to get a valid confidence interval. And there's going to be no black box, nothing magic about it. Very easy to understand. So very usable in an environment where understandability is important. On the other hand, in some cases, you want to get fully personalized predictions. Generally there, the existing literature for non-parametric estimation that gives you asymptotically normal predictions would be kernels and k-nearest neighbors. Those algorithms fall apart with like more than 3 or 4 dimensions. They just do very badly. And the problem is that if you say you had 100 dimensions of covariates, you can't be close. If you're trying to be close in 100 dimensions, you're not very close in any. So what we want to do there is bring in random forest, which is essentially an adaptive nearest neighbor algorithm, but we want to develop the asymptotic theory for it. So our contributions are to we're going to actually change the existing machine learning methods of trees and forests to achieve these goals. They don't work unless you change them, and they don't work well unless you change them even more. We're going to deal with an issue that there's no observed ground truth. That is, if you're trying to do causal inference, you don't actually know what the right answer is. And our methods are going to provide valid confidence intervals without sparsity. So this is a picture of a regression tree, and it's basically you use a tree to divide the data according to covariates, x1 and x2, and then within each leaf, you make a prediction. So this is a picture of what it looks like in covariate space, x1 and x2. And so within each region, you're going to make a prediction just based on the average value of your outcome within the region. Okay? So they're very easy to interpret. This is, in the pure prediction case, the prediction is just an average within a region. So for the economist in the room, it's like running a regression with dummy variables for each of these regions, but the data told you which dummy variables to do. The alternative might be to divide it into deciles by deciles, but then you'd have 100 parameters instead of, however, there's 7 here. So this is actually going to be much better. But the problem with this is that I peeked at the data in order to determine what these boundaries should be. And so if I had a bunch of high epsilon or low epsilon guys in this region, I'm going to find that, and this estimate's going to be biased. Okay? So that's the problem with it. So I need to fix that bias if I want to provide valid confidence intervals. So what I'm going to do, this is a notation for causal effects. I'm going to write down yi is going to be yi of 1 if you were treated, yi of 0 otherwise. And the counterfactual treatment effect is yi of 1 minus yi of 0. You only observe either yi of 0 or yi of 1, but you never observe tau I for any particular unit. So what we're going to do is we're going to change the standard recursive partitioning algorithms to do a few different things. First of all, we're going to directly estimate treatments within a leaf. Second, we're going to modify our splitting criteria to focus on treatment effect heterogeneity instead of predicting outcomes. Our cross-validation criteria is going to have to estimate the ground truth. We're going to have to deal with the fact that I don't observe the treatment effect for any individual. And we're going to use what we call honest trees. That is, we're going to use one sample to decide how to do the splits and another sample to estimate the effects. And that's going to get rid of the bias, because when I estimate the treatment effect, I'm going to be using a set of partitions that were determined on an independent data sample. Now, you might think, oh my gosh, I'm throwing away half my data, but my point would be, wouldn't you rather learn something true on half your data than learn something false on all of your data? And in the big data setting, this is often the right way to go. So here's an example. I did an experiment where I flipped the first and third positions for Bing search. And what I found is when you take an algorithmic link from the first to the third position, you lose 13.6 percentage points of click-through rate. So what this looks like when I then go and see if this is heterogeneous is I get this tree. Within each leaf of the tree, I'm going to get a different average treatment effect, a different standard error. Okay, and these standard errors are going to be valid, again, because I split my sample. So I'm going to find that for some queries, there's no treatment effect. These are image celebrity queries where people didn't really care about the algorithmic results. And for others, I get very strong treatment effects, like informational queries where the ranking matters a lot. Then what I look at and see is I see how much does the bias matter. So what if I estimate my effects in the same data that I use to make my splits versus when I'm honest and I use a new sample? So it's a little hard to see from the table of numbers, but my mean was negative 0.136. And so here, the ones in red are ones where you get a more extreme result in the training sample. Kind of amazing is you get a couple 100,000 observations here, but yet there's only like 20 odd leaves, but you still get a substantial bias. So the bias doesn't go away with big data. Because you basically what my tree is so good at finding little clusters of guys that have unusually large or unusually small treatment effects that you still get a bias. What if I want personalized predictions? Well, there's something called the random forest, which is super popular. It works really well in practice. It's a predictor. And what it basically does is it takes a whole bunch of different trees and averages them up. It also builds very deep trees, so it tries to make the leaves really tiny. So and each tree differs because you're subsampling the training set. We can think of this as an adaptive nearest neighbors algorithm. Each tree is going through and splitting on covariates, finding covariates that are important for heterogeneous treatment effects. And then it's going to figure out who are the neighbors that are actually relevant for heterogeneous treatment effects. And it's not going to try to match you on covariates that aren't important. So if you have 1,000 covariates, it's very important to find the 10 covariates that matter and not try to match on 1,000. And this algorithm is going to do that for you. So we developed something called a causal forest. We're going to use subsampling to create alternative trees. A cool thing now is that there's actually no cost to being honest, because I was subsampling anyways. So I take one subsample to build the leaves, another subsample to do my estimates. I can use different subsamples each time, so I use all my data, but I get rid of the bias. And so out of that, what we're going to do is we're going to have these causal forests that estimate heterogeneous treatment effects. So if you show me your vector of covariates, I can predict your personalized treatment effect. So these results, we're going to have a central limit theorem, our first asymptotic normality results out there for random forest. And so one reason I said before nobody cared, so not a lot of people were working on this, but the standard algorithm that's built into R, this was false. The results are not asymptotically normal. The reason is that are bias dominated. The bias is too big. But they're good for mean squared error, but they're not good for asymptotic normality. But making them honest, among other things, gets me asymptotic normality. It makes the bias go to 0 fast enough. If you want something to be asymptotically normal and centered on 0, the bias has to go to 0 fast enough. And it doesn't just have to be consistent. The bias has to go fast enough. And so we do that with our honesty. And then we can get confidence intervals for causal effects. So here's just a picture we're comparing to k-nearest neighbors, because k-nearest neighbors is something where asymptotic normality in principle works. This is the truth. This is our estimates, the colors of the treatment effects. This is K and N. K and N is much messier because it doesn't know which neighbors are important to match to. We're actually better in terms of both bias and variance than K and N. And if you go up to like 20 covariates, K and N falls apart because it's just not finding which neighbors are important while we kind of hang in there. So basically, with these methods, you can get personalized predictions, and in principle, you can build them into an experimentation platform. And so that's what a couple of the big tech firms are working on right now, and I'm collaborating with some of them to try to take this and into their platforms. What they're going to do is whenever you run a test, we'll produce the subgroups that have bigger or smaller treatment effects. But in terms of predicting long-term effects, this still has a lot of limitations, because all I've done so far is say who is affected, and then you still have to pair that with a behavioral model. So the last approach, which I won't have time to show you the details of, is joint with Denis Nekopolov. And so this approach, again, is the sort of the standard econometric approach, would be to actually assume profit maximization. In our recent work, we specify a set of objectives. And we estimate a Bayesian model where we estimate the actual preferences of the advertisers. And so then what we can do is, once we have that model, if we run any experiment, we can look at the short-term metrics and we can see how different types of advertisers are affected. And then we can say, all right, well, our model is going to tell me if you were affected this way, this is how we expect you to respond. So it's a way to basically take a short-term experiment and calculate a new equilibrium. Again, this is the one that's, I think, the most scientifically valid. It's the only one that really incorporates all the things we know are going on in practice. But these kinds of models are kind of hard to sell in the real world, and hard to have influence. So I've had mixed success, some successes, some failures with trying to get people to adopt those types of techniques. So in sum, this is a bunch of different techniques ranging from statistical theory to machine learning, experimentation, and structural Bayesian models, all trying to solve the same problem, which is just to say, look, if I change something in a marketplace, what's going to happen? Surprisingly hard problem. So I'm happy to take questions. Yeah.
So you talked a lot about making an experiment to a market and see, and that's a hard enough problem already. I still wanted to get your thoughts on, suppose you have no specific experiment that you want to run, but you just want to optimize the entire market, and hopefully you don't want to run too many tests, right? So you can't possibly test every single design. Can you comment a little bit about how you would set out to do that while still trying to do some kind of experimentation?
Sure. So actually, the paper I have with Dennis, as well as some other stuff that I've done, and recently a few other people, economists, have gotten excited about as well, is that you can actually learn a lot about people's preferences even if you didn't design an experiment for that purpose. So, if you think about Bing or Facebook or Amazon or Google, they're changing things. They're changing little things all the time, but every couple of weeks they're actually making fairly significant changes that really, changes in the quick prediction algorithms, changes that really, at the individual level, create quite a bit of shocks. So the aggregate effect might be small, but at the individual level, there's a lot of shocks. So if I can see how an advertiser responds to these shocks, even though the experiment wasn't designed to shock them, then I can still learn about their preferences. And that's what Dennis and I do. We actually have one approach where we just sort of assume that everything that shocks an advertiser is what we call exogenous, and see what happens with that. But another approach is more motivated by what economists call instrumental variables, where we try to only use the noise in the data that was induced by an experiment or by what we know to be a change that was not related to the advertiser. So if I know that every 2 weeks there was a big change in the system, then that shock I can know the day before, the day after, and I can see, this shock raised this advertiser's prices, it did these things to its objective function. And then I see how they respond to that. So this is like reusing existing experiments. And it's actually quite a powerful idea because, say, Google's running 10,000 experiments a year. They may never do the experiment we're interested in scientifically, but if we can find a way to use that variation, we can actually learn a lot about what's happening in practice. So there's a few people, Justin Rao has a paper on this. I did something on this a couple years ago, with position effects for ads, for example. So, yeah.
I guess there's another issue that probably you confront a lot is a lot of tests going on in parallel. So can you use the kinds of methods you've discussed to deal with interaction effects across experiments in a sort of post-hoc way? Is that something you've done? Or?
I haven't done that. I think that it is actually for the heterogeneity of treatment effects thing. If you wanted to think about another application, you could actually think of like the covariates as being all the different experiments you were in. Exactly. Yeah. So that's been suggested once or twice, but I haven't gotten to that yet. But I think it's an interesting idea. Yeah.
So, in a lot of these spaces, there are competing firms, like let's say sponsored search. And if you do these experiments, and you don't do it at the whole level, you do it at the 1% level, then have you thought about the strategic effects of the response of the other guys once you take it to the large?
Well, so the work with Dennis, and I have to be honest, we have not succeeded in computing a new equilibrium for the entire Bing ad platform. We haven't tried that hard because it's more useful in practice than it is for our academic paper. But in principle, if you know everybody's objectives, you can recompute the equilibrium for the whole system. But that's actually, of course, computationally quite hard because there's millions and millions of bids that are taking place. And that actually gets back to another, I didn't have time to talk about it, but another reason it's interesting to think about these these communities and testing interactions between communities is that, well, suppose I use a community detection algorithm to find pretty, isolated communities, and then if I can reject the hypothesis that these guys interact with each other, then maybe that motivates a computational algorithm that ignores certain links, and then if I have a block diagonal type of strategic matrix, that's a much better thing to compute than a full equilibrium among zillions of things. So that's I think this is actually someplace again where though publishing in computer science journals or slightly more practical disciplines is useful, because econometricians tend to not be very forgiving of approximations for bizarre historical reasons, where this is obviously a place where you want to make approximations, and it shouldn't hurt you so much. Eva?
Actually, reacting to your last comment, you're making approximations, I would say, all the time, because you don't actually, I don't believe you really know or can infer the objective function of the user, and then, in fact, even the format on which you put the utility function is a particular form, and I think real-life utilities are more complex than that.
So economists are a little strange, and I've come to, as you step outside your discipline, you appreciate more the weirdness of each discipline. So we will, make there's certain kinds of assumptions we're happy to make, and then we stick to them, like this is our functional form, and they profit maximize, and even this is normal, and we're all happy with that, but like we can't have an approximate equilibrium. That would be bad, 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 and it's obviously stupid, but these are our conventions.
So, my question would have been, can you say anything about what your conclusions mean if you take into effect that you don't actually know, you don't exactly know. It is roughly the utility, not necessarily exactly the utility.
Yeah, so I would say that there's a lot of conventions that we have for evaluating empirical work and evaluating its robustness, but it's a lot of it is arguing and defending and, so we're not super systematic with that. And I think that's actually a criticism I have of econometrics as a whole, is that we're not systematic at model robustness, we're not systematic at model selection, and that's partly because we kind of started from a position where we were digging in our heels and defending these assumptions and then getting exact results for them. So we're not really able to admit it in a paper, therefore we haven't developed good formal techniques for doing it. Yeah.
So following up on Hannah's question, if you cannot compute the equilibrium probabilities, the advertisers also won't compute it. So have you thought about going beyond the equilibrium? I think it's a very important problem to understand this. So have you thought about how to go beyond the equilibrium to some other types of responses?
Yeah, well, and I think honestly, in the search setting in particular, they're really not, when you talk to them, when you look at the algorithms that are used by the bidding agents and so on, they're not strategic. They're all just best responding to the current set of circumstances. None of the guys are very strategic. So I think that is a very important thing. In some ways, it makes things easier, because if you just assume everybody's kind of doing some iterated best responses, that might be a better way and a more realistic way. Because it's like with these things, everybody's using these bidding agents, and then the bidding agents are competing against each other. And if we know those bidding agents aren't factoring in certain things, then why should we factor them in, in our computations? So again, though, I think if we were writing in that direction, luckily I think Dennis has now become more of a computer scientist too, so maybe we'll take some of that to the disciplines that are more open to to those techniques. But where we started when publishing in economics journals, those are harder papers to write. Not to emphasize this too much, but it's this partly a meta conversation we can have about what the strengths and weaknesses of different approaches are, which also helps you think about what are open areas. Economists didn't touch these areas because we have these religious beliefs, and then there's other things where, maybe other disciplines haven't looked at as much, like the causal inference and the asymptotic normality in machine learning is something that people just didn't look at because they weren't interested.